Hello, my name is Kevin Shabahang. Here I will present work applying a new model I helped develop to the free association task and comparing its performance with some state-of-the-art semantic representation frameworks. This is a pre-recorded presentation for the 2021 Mathematical Psychology and ICCM conference. I did this work with the help of Professors Hyungwoo Kim and Simon Dennis. In a free association task, you are given a cue and are asked to report the word that immediately comes to mind. Over many trials and participants, stable patterns of association emerge between concepts. These patterns of association continue to evade explanation even by the state-of-the-art semantic representation scheme. In this talk, I will first briefly discuss some influential models of semantic processing and how they could be used to model free associations. And then I'm going to present our own dynamic systems view that treats free associations as steady states. We consider two classes of modeling: high-level descriptive accounts and low-level process models. We replicate results from Griffith and colleagues who used LSA and the topics model as an anchor point and extend the work by considering another high-level model called Word2Vec. Finally, we consider two process accounts, Beagle and a dynamic eigennet. We characterize both LSA and the topics model as high-level accounts because they don't specify an incremental learning algorithm. Word2Vec has face validity as a process model, but it requires many passes through the training data to learn its structure. This is also true of the topics model when using Gibbs sampling. In all four baseline models, the word by context statistics are somehow abstracted to encode more semantically relevant representations. Here we explore what happens when we defer abstraction until retrieval and only encode simple word-by-word co-occurrence statistics. During retrieval, a cue pattern then sets the initial conditions for a relaxation process to yield an abstraction. In LSA, you take a set of documents and count the number of times each word occurs in each document and tally it up in a matrix. Each word gives you a vector, a point in high-dimensional space. Then you approximate the original space by squeezing it into lower dimensions. One way semantic information emerges through dimensionality reduction or is enhanced by it is through increasing similarity between items that have transitive associations. For example, given you studied the following two sentences, each in a different context or document, notice that the word feathers occurs in both contexts. Dimensionality reduction merges the context boundaries by pulling words that share directly co-occurring neighbors closer to one another. Although eagle and hawk didn't co-occur together in the same context, they are pulled towards each other through feathers. An alternative approach is to treat each document as a probability distribution over a set of latent topics. We assume that a document is generated by iteratively sampling a topic from its topic distribution, followed by a word sampled from a conditional distribution of words over the topics. The topics model decomposes the word by document matrix into a matrix of conditional probabilities of words given the topics and another matrix of conditional probabilities of topics given the documents. In the continuous bag of words variant of Word2Vec, random slices of text with a fixed size window are used to fine-tune the system by treating the word in the center as a to-be-predicted target and its surrounding words as prediction signals. Activation from those surrounding words propagate forward as input and project to a hidden layer of lower dimensionality. The hidden layer then projects to an output layer that gives a probability distribution over possible target words, conditioned on the context words. The network is trained to maximize the conditional probability of the target given the context. In addition, a set of irrelevant words are sampled for each context target pair, and the network is also simultaneously trained to minimize their conditional probability given the same context words. Training is done using stochastic gradient descent, using simulated annealing. In Beagle, first a set of placeholder vectors, labeled here as P, are initialized and used to form a new set of vectors called item vectors. The item vectors encode each word's history of usage with other co-occurring words in the corpus. As with Word2Vec, Beagle assumes a fixed size window, but instead of randomly sampling slices, you slide the window continuously through the corpus from start to finish. At each slice, the item vector for each word in a window is updated by accumulating the placeholder vectors for the other words in the window into its item vector. Over time, the item vectors stabilize to patterns that capture the history of usage of the words in the training corpus. All these approaches reduce the original word by context statistics into a more abstract representation. One limitation is that the representations are static and require further mechanics for contextual grounding. An alternative is to abstract at retrieval instead of encoding. Take the two contexts I introduced earlier. We can represent the connections between words that occur in the same context together in an associative net. An associative net is characterized by a memory and a momentary state. Here, the memory is a word-by-word matrix of weights derived from co-occurrence counts between words across a sliding window. The state is represented by a vector of the same dimensionality as the number of unique words in our vocabulary. We can cue the system by initializing its state to have a cue word active, such as eagle. We run a single iteration by multiplying the state with the matrix and unit normalizing the outcome. This spreads the activation from the original cue word, eagle, to the words with which it's directly connected. That is, words it co-occurred with in the same context, such as a sliding window. These connections are sometimes called syntagmatic. Now, if we take the output from the first iteration and use it to iterate a second time, because feathers became activated after the first iteration, this time it activates its neighbors, such as hawk. Although hawk did not co-occur with eagle, it became activated through mediating associations. Hence, it's a kind of latent associate of eagle. We run the iterations many times until the system settles to a steady state or an equilibrium. As the system approaches its steady state during retrieval, latent relationships between words emerge. Our weight matrix is square and symmetric, which means it can be decomposed into a set of eigenvectors, denoted by the capital E, and a set of eigenvalues, denoted by a capital lambda. The original matrix is the sum of the outer products of each eigenvector weighted by its corresponding eigenvalue. Suppose x0 is the state vector initialized with a given q. A single iteration is shown on the right-hand side of the following equation in terms of the eigenvectors. It says that the output is the sum of the eigenvectors of the original matrix, each weighted by the corresponding eigenvalue, and the dot product between the input and the eigenvector. After t iterations, the eigenvalues in the equation are raised to the tth power. But because the eigenvalues fall in magnitude from the first eigenvalue to the last, in the limit, the output of the system will always correspond to the dominant eigenvector. This limits the associative net as a memory system. Models like the brain state in a box and the Hopfield net enable other steady states by introducing nonlinearities. We propose an alternative solution which preserves the system's linearity. In what we're calling the dynamic eigennet, the outer product of the initial state is added to the weight matrix before recurrence and is removed after the system settles. Here, the right-hand side shows how adding the outer product introduces a new term. The parentheses emphasize the scalar terms in the equation. In a dynamic eigennet, we not only have the eigenvector term, as we did in the linear system, but we have an additional term corresponding to the initial state. The initial state is added to the output, weighted by its dot product with the momentary state. This additional term acts as an anchor to prevent the state from moving too far into the distance. It changes the Basins of attraction in the original space. Let E prime and lambda prime correspond to the dominant eigenvector and value of the modified weight matrix. Then in the limit, the system converges to the sum of each eigenvector weighted by its eigenvalue and dot product with the momentary state, plus the initial state weighted by its dot product with the momentary state. The right-hand side shows this term corresponds to the dominant eigenvector of the altered matrix. Before any retrieval, we need to encode the word-by-word associations into a matrix. First, we count the number of times pairs of words co-occur over a sliding window through the corpus. One of the requirements for the dynamic eigennet is for the eigenvalues to decrease slowly, but using the raw co-occurrence counts yields a sharp drop in the eigenvalues. We only keep associations where both words are in the top D co-occurrence ranking with respect to each other, in which case we set the associative weight between the pair of words as the log of their co-occurrence count. We use a D of 64 so that each word is associated with at most 64 other words, and those words most commonly co-occur with it. We call this the max degree rule. The max degree rule flattens the eigenspectrum. Here is a subnetwork of the topmost active words across iterations after queuing the system with the word eagle. The direct connections between eagle and the other nodes are shown in yellow. I lesioned the memory to mimic the case where eagle and hawk are not directly connected. All the direct neighbors of eagle become activated after a single recurrent iteration, but notice how semantically relevant words like fly, hawk, and robin are not active. After a second iteration, fly, hawk, and robin become activated, and they remain active at the steady state. We can sort the steady state activations in descending order and give each word a rank. In this case, the word wing of rank 1 is the most active word and would be taken as the system's response or free associate. Alternatively, we can assume a secondary choice process that maps the activations to a probability distribution over the responses. Here we simply examine the rank, but if we were to have an additional choice layer, lower rank values would correspond to more probable choices. In LSA, Word2Vec, and Beagle, the vector cosine is used as a measure of similarity between words. For free association, we take the cosine of each Q word with all other words. We then check how far down the similarities the most common response from human free association lies for each Q. The same approach is used in the topics model, but instead of cosines we use the conditional probability of each word in our vocabulary given each Q. Griffith and colleagues reported a median rank for the first associate of 31 out of 4,470 for LSA and 18 for the topics model. The number of times the free associate ranked 1 was 11.54% for LSA and 16.15% for the topics model. We matched their corpus as best we could and used the 5 models we have discussed to predict the free associations. Here, for each model, I'm showing the percent of times the most common human free associate ranked the highest, followed by the median rank of the most common associate. We get similar scores for LSA and the topics model as what was reported by Griffith and colleagues, suggesting our corpora are well matched. In terms of the first associates, Word2Vec outperforms topics, while the dynamic eigennet outperforms Beagle and LSA. In terms of the median ranks, Word2Vec outperforms all other models. LSA performs better than dynamic eigennet, but the dynamic eigennet still outperforms Beagle. In conclusion, the descriptive accounts outperform the process models. In LSA and topics, it may be that the word-by-document input provides more constraint than a sliding window. In Word2Vec, it's likely that the negative sampling optimization leads to better performance. The dynamic eigennet performs slightly better than Beagle. Because dynamic eigennets abstract at encoding, they are more suitable for context-dependent processing. But overall, about 80% of the first associates were not predicted by the best model. One possibility is that the language environment of the participants was not fully captured by our corpus. Another possibility is that extra-linguistic information is necessary, such as visual or affective information. In conclusion, dynamic eigennets provide a good process model of the task, but we still have a long way to go before we can fully explain free associations. Thank you.